September 17, 1944. The Dutch-German border near Nijmegen. General Major Hans von Tettau stood on the eastern bank of the Waal River, studying the smoking remains of the bridge his engineers had just demolished. 3 massive stone spans lay in the river, twisted steel jutting from the water like broken teeth. The bridge had taken 4 years to build in peacetime. His engineers had destroyed it in 40 minutes. Von Tettau allowed himself a thin smile of satisfaction. The Americans would reach this river within days, perhaps hours. But without a bridge capable of supporting their heavy armor, they'd be stuck. Building a replacement would take months, maybe longer if German artillery kept harassing the construction site. This river would be the Americans' problem for the rest of 1944. Herr General, his engineering officer reported, the demolition is complete. The Americans will need substantial time to restore crossing capability. Our calculations suggest minimum 3 months for temporary restoration, 6 months for full reconstruction. Von Tettau nodded. 3 months was an eternity in modern warfare. By then, winter would have arrived, the offensive would stall, and Germany would have time to regroup. The destroyed bridge was worth more than a panzer division. What General Major von Tettau didn't know, what none of the German commanders who had spent the summer of 1944 systematically destroying every bridge in France, Belgium, and Holland could have imagined, was that American engineers were carrying the solution in the backs of their trucks. A solution so simple, so modular, so insanely effective that it would render bridge demolition almost pointless. Within 72 hours of reaching that river, American engineers would have a bridge across it capable of supporting 40-ton tanks. Not a rickety temporary structure, but a legitimate military bridge. And they'd build it using a system so brilliant that even German engineers who examined captured components couldn't believe it worked as well as it did. This is the story of the Bailey Bridge, a weapon that never fired a shot but won battles anyway. How a British civil engineer's simple idea became America's secret weapon for mobility. How German generals' carefully planned defensive lines became speed bumps. And how a bunch of American GIs with wrenches and determination built armies overnight while their enemies watched in disbelief. The Bailey Bridge wasn't even an American invention. It was designed by a mild-mannered British civil engineer named Donald Bailey in 1940, during the dark days when Britain stood alone against Nazi Germany. Bailey, who'd spent his career designing roads and drainage systems, was thinking about the military's bridge problem. Traditional military bridges were heavy, complex, and required specialized equipment to assemble. Pontoon bridges were faster but couldn't support heavy loads and were vulnerable to current and enemy fire. Fixed bridges took forever to build and required skilled engineers. The British Army needed something better, something that regular soldiers could assemble quickly under combat conditions. Bailey's solution was so elegantly simple that military engineers initially dismissed it as too basic to work. He designed a bridge made from prefabricated steel panels, each panel measuring 10 feet long by 5 feet high and weighing just 570 pounds. 6 men could carry one panel. The panels connected to each other with steel pins that you could hammer in by hand. No welding, no riveting, no specialized tools. Just panels, pins, and determination. The genius was in the modular design. Need a stronger bridge? Add more panels on top of each other to create multiple trusses. Need a longer bridge? Keep adding panels end to end. Need even more strength? Add panels side by side. The same basic components could create bridges ranging from 10 feet to over 200 feet long, capable of supporting loads from light vehicles to the heaviest tanks. The British tested the first prototype in 1941, and military engineers lost their minds. You could build a 60-foot bridge in 3 hours with a squad of untrained soldiers. A 120-foot bridge in 10 hours. And these weren't flimsy structures. They were legitimate bridges that could handle the weight of a Churchill tank, 40 tons, or even heavier loads if you doubled or tripled the panels. The British immediately ordered mass production. By 1942, Bailey bridges were appearing across North Africa as British forces pushed Rommel back across Libya. American engineers, watching their British counterparts slap these things together in record time, basically said, "Holy crap, we need those." The U.S. Army licensed the design and started cranking out Bailey bridge components by the thousands. American factories, already geared up for mass production, could produce these panels faster than almost any other military equipment. They were just steel panels with holes. Any fabrication shop could make them. By 1943, American engineering units were receiving Bailey bridge sets as standard equipment. But the real test would come in 1944, when American armies broke out of Normandy and started racing across France. Because the Germans had a plan. A very logical, very thorough plan. They were going to destroy every goddamn bridge in Western Europe. The German strategy for defending France in 1944 was actually pretty smart on paper. They couldn't stop the Allied invasion at the beaches. The Allies had too much firepower, too much air superiority, too many troops. But they could slow down the Allied advance to a crawl by destroying infrastructure. Every bridge over every river, stream, and canal in France was rigged with demolitions. Railway bridges, highway bridges, farm bridges, ancient stone bridges that had stood since Roman times, all of them got wired with explosives. The plan was simple. As German forces retreated, they'd blow the bridges behind them. The Allies would get stuck at each river line, giving German forces time to establish new defensive positions. This wasn't theoretical. The Germans had pulled off exactly this strategy in Italy in 1943-44, where they'd turned the Italian peninsula into a series of fortified river lines. Every time the Allies advanced, they'd hit a destroyed bridge and a German defensive position on the opposite bank. Rebuilding under fire was nearly impossible, so the advance would stall until engineers could find a way across or Allied forces could outflank the position. The strategy had worked brilliantly in Italy. It should have worked in France. German engineering officers had calculated that each destroyed bridge would cost the Allies approximately 2 to 3 weeks of delay. Time to build temporary crossings, bring up bridging equipment, and get supplies flowing again. With dozens of major rivers between Normandy and Germany, that added up to months of delay. Oberst Friedrich Schulz, chief of engineering for Army Group B, had personally supervised the preparation of demolitions along the Seine, Marne, Meuse, and Moselle rivers. His after-action report from July 1944 expressed confidence. All major crossings prepared for demolition. American advance will be significantly hampered by lack of bridging capacity. Estimate minimum 90 days delay accumulated across multiple river lines. The Germans weren't being arrogant. They were making reasonable calculations based on their experience. Building bridges was hard. Building them under fire was harder. Building them fast enough to maintain offensive momentum was nearly impossible. Or at least, it had been impossible before the Bailey Bridge. The American breakout from Normandy in late July 1944 caught the Germans by surprise. Operation Cobra shattered German defensive lines, and American armored divisions started racing across France at speeds that shocked everyone, including American commanders. Patton's Third Army was covering 50, sometimes 60 miles per day, absolutely tearing through German rear areas. But the speed also created a problem. The faster you advance, the faster you hit destroyed bridges. And boy, did the Americans hit destroyed bridges. Every river, every stream, every drainage ditch with a demolished crossing. The Germans had been thorough. At the Saloon River on August 1, 1944, lead elements of the 4th Armored Division rolled up to what had been a substantial highway bridge. Past tense, it was now a pile of rubble in the river, demolished so thoroughly that you couldn't even tell where the original structure had stood. The division's operations officer radioed back to headquarters. Bridge destroyed. Estimate 3 weeks to restore crossing capability. The response came back within an hour. Engineer battalion en route. Expect crossing by 1800 hours. The operations officer thought somebody was crazy. It was currently 0900. That gave the engineers 9 hours to build a bridge capable of supporting Sherman tanks. That wasn't possible. That was absolute fantasy land. At 1,750 hours, 10 minutes ahead of schedule, the first Sherman tank rolled across a brand new Bailey Bridge spanning the Saloon River. The entire bridge, 120 feet long and rated for 40-ton loads, had been assembled in 8 hours and 40 minutes by one company of combat engineers. The German defenders on the opposite bank had watched in absolute confusion as American trucks arrived, disgorged what looked like metal panels, and then American soldiers started assembling these panels like a giant erector set. The Germans had shelled the construction site, but the engineers just kept working. Casualties were replaced. Damaged panels were swapped out. The bridge kept growing. A captured German lieutenant, brought back for interrogation that evening, kept insisting there had been a misunderstanding. The bridge we destroyed this morning, it is impossible to replace so quickly. Impossible. Your engineers must have had that bridge prepositioned. Yes. They brought a complete bridge on trucks and simply placed it. When American engineers explained the Bailey system, the German officer refused to believe it. Bridges couldn't be built that way. Bridges required complex engineering, heavy equipment, weeks of work. You couldn't just assemble them from panels like children's toys. But that's exactly what American engineers were doing, and they were getting damn good at it. The Bailey Bridge system came with detailed instruction manuals, but American engineers quickly developed their own techniques and shortcuts. They figured out that you could pre-assemble sections on the riverbank, then use rollers to push the completed sections out over the gap. They discovered that with enough men, you could build even faster by working on multiple sections simultaneously. Lieutenant Colonel David Pergrin, commanding the 291st Engineer Combat Battalion, became something of a legend for Bailey Bridge construction. His unit would eventually build over 60 bridges during the European campaign, many under direct enemy fire. Pergrin's philosophy was simple: speed is armor. The faster we build, the less time the Germans have to shoot at us. His battalion developed what they called the Pergrin method, a streamlined assembly process that could cut construction time nearly in half. Instead of following the manual step-by-step approach, they'd pre-stage components in the order needed, assign specific teams to specific tasks, and work with assembly line efficiency. At the Meuse River in August 1944, Pergrin's battalion built a 180-foot triple-single Bailey Bridge, 3 panels high, 1 panel wide, in 14 hours while under intermittent artillery fire. The bridge was strong enough to handle the heaviest American tanks and was built so well that it was still in use for civilian traffic into the 1950s. The Germans couldn't wrap their heads around this. Their own military bridging systems required specialized equipment, bridging trains with heavy steel components that took days to position and assemble. The Bailey system could be transported in standard trucks and assembled by regular engineers with basic tools. General Lieutenant Walter Model, commanding Army Group B during the Normandy campaign, was receiving increasingly frantic reports from his engineering officers. The Americans were crossing rivers within hours of arrival. Defensive lines that should have held for weeks were being breached in days. Model initially blamed his subordinates for inadequate demolitions. Then he saw a Bailey Bridge himself. In early September 1944, while conducting a frontline inspection near Nancy, Model observed American engineers constructing a Bailey Bridge across the Moselle. Through his binoculars, he watched as the structure grew with impossible speed, panels being added, the bridge extending across the water like a living thing. Model turned to his chief of staff. "What is this? How are they doing this?" Nobody had a good answer. German intelligence had reports of the Bailey Bridge system, but seeing it in action was different. The speed of construction seemed to violate fundamental principles of engineering. Yet there it was, growing before their eyes. Model ordered his artillery to target the bridge site. German guns hammered the position for 30 minutes. When the smoke cleared, the Americans were still building. They'd lost some men, damaged some panels, but the bridge continued to grow. Model realized with cold certainty that bridge demolition was no longer an effective defensive strategy. His report to OKW, German High Command, was blunt. Enemy possesses rapid bridging capability that negates river line defense. All major crossings destroyed per plan, yet enemy maintains offensive momentum. Request immediate information on enemy bridging systems and countermeasures. The countermeasures never materialized because there weren't any good ones. The Bailey Bridge was too simple, too fast, and too effective. You could shell the construction site, but American engineers would just work through the bombardment. You could try to defend the river line, but American artillery and air support would suppress your positions. You could destroy the completed bridge, but the Americans would just build another one. The mathematical reality was brutal. It took German engineers 30 to 40 minutes to demolish a bridge with pre-placed charges. It took American engineers 8 to 12 hours to build a Bailey Bridge replacement. That was an acceptable trade ratio from the American perspective, especially since the Germans couldn't destroy the same crossing twice. By September 1944, American forces were advancing so fast that German demolition teams couldn't keep up. Some bridges were captured intact because retreating German forces didn't have time to blow them. Others were only partially destroyed. Maybe one span dropped but the others intact, and American engineers would just slap Bailey panels across the gap. At Remagen in March 1945, American forces famously captured the Ludendorff Bridge intact, the only Rhine crossing that the Germans failed to destroy. But what's often overlooked is that within 48 hours, American engineers had constructed 2 Bailey bridges adjacent to the captured bridge, because they knew the damaged Ludendorff could collapse at any moment, which it did 10 days later. The Bailey bridges kept traffic flowing without interruption. The versatility of the Bailey system was mind-blowing. Need a bridge across a small stream? Single configuration, built in 2 hours. Need a bridge across a major river capable of handling constant tank traffic? Triple configuration, built in 24 hours. Need an emergency bridge right goddamn now? Engineers could build a single Bailey in under 90 minutes if they pushed hard and caught some luck. The components were interchangeable and reusable. If a bridge got damaged by artillery or bombing, you could replace individual panels without rebuilding the whole structure. If you didn't need a bridge anymore, you could disassemble it and truck the components to the next river. German bridges, once destroyed, were just rubble. Bailey bridges were resources that could be redeployed. American logistics officers loved the Bailey system because it simplified supply chains. Instead of needing different bridging systems for different situations, they could stockpile Bailey components and use them for anything. Every engineer battalion carried Bailey bridge sets as standard equipment. Rear area depots stored thousands of panels, ready to be trucked forward on demand. The production numbers were staggering. American factories were producing over 1,000 tons of Bailey bridge components per week by late 1944. That was enough material to build roughly 15 to 20 complete bridges weekly. The components were so simple to manufacture that production could be easily scaled up or down based on need. Private First Class Mike Trevino, an engineer with the 2nd Armored Division, described the experience of building Bailey bridges under combat conditions. It's organized chaos, man. You've got shells landing, guys yelling, trucks everywhere, panels coming off trucks and getting assembled faster than you can believe. Your job is simple. Grab a panel, carry it to position, pin it in place, grab the next panel. Don't think, just work. The faster we build, the faster we get out of there. The Germans couldn't believe how fast we worked. I remember one time, we're building a bridge and there's German troops on the other side, maybe 400 yards away, just watching us. They could have shot at us, but I think they were too stunned. We built that bridge in 6 hours, got our tanks across, and kicked their asses. Pretty sure those German soldiers went back and told their officers, the Americans have magic bridges. That's what it looked like, magic. The psychological impact on German forces was significant. Defensive strategies built around river lines became increasingly ineffective. German units would retreat to a river, blow the bridges, and start preparing defenses, only to discover American tanks crossing on Bailey bridges before the defensive positions were even complete. This forced the Germans into increasingly desperate tactics. Some units would leave behind dedicated artillery observers with the sole mission of calling fire on bridge construction sites. Some would position snipers to target American engineers. Some would float mines downriver hoping to damage bridge supports. Nothing worked consistently because American engineers were too fast and too determined. The Bailey Bridge also solved a massive logistics problem that's often overlooked: bridge classification. Military bridges are rated for the weight they can support, measured in class numbers. A Class 40 bridge can support a 40-ton vehicle. The problem in 1944 was that American armor was getting heavier. Sherman tanks were around 30 tons, but newer models and tank destroyers were pushing 40-plus tons. Traditional military bridges were fixed in their capacity. A pontoon bridge could handle light loads, but not heavy armor. The Bailey system was adjustable. Need Class 40 capacity? Build a double-double configuration. Need Class 70 for really heavy loads? Build a triple-double. Same components, different arrangements, customized capacity. This flexibility meant American armored divisions could keep moving without worrying about whether bridges could handle their vehicles. The engineers would show up, assess the gap, and build whatever was needed. No guesswork, no trial and error, just math and manpower. British Field Marshal Bernard Montgomery, commanding 21st Army Group during the European campaign, was initially skeptical of American engineering capabilities. The British had been using Bailey bridges longer and considered themselves the experts. Then he watched American engineers work during the crossing of the Rhine in March 1945. American engineers built 62 Bailey bridges across the Rhine and its tributaries in the first 2 weeks of the offensive. 62 bridges. Some were small, single-span crossings over minor tributaries. Others were massive. The bridge at Wesel was over 400 feet long and required multiple Bailey bridge sets connected together. All were built under combat conditions, with German artillery and occasional air attack. Montgomery's engineering officer reported, "The Americans approach bridge construction with industrial efficiency. What would take our units 18 hours, American engineers accomplish in 12. Their organization, their manpower allocation, their willingness to work under fire, it's quite remarkable. I believe the Bailey Bridge has proven more valuable than many weapon systems in maintaining offensive momentum." That's high praise from the British, who generally viewed American military capabilities with polite skepticism. But even the Brits had to admit, the Americans had taken the British invention and turned it into an art form. The speed records became a source of pride among American engineer units. Battalions would compete informally to see who could build the fastest bridge, who could work under the worst conditions, who could improvise the best solutions. The 291st Engineer Combat Battalion claimed they'd built a 60-foot bridge in 90 minutes. The 51st Engineer Combat Battalion said they'd done it in 85 minutes. These weren't official records, just engineers talking shit and trying to one-up each other. But the competition drove innovation. Engineers developed new techniques, better organization, smarter staging of materials. They figured out that you could use local labor, German POWs or French civilians, to handle basic materials transport, freeing up trained engineers for specialized tasks. They learned that pre-assembling larger sections off-site and trucking them to the location could save massive amounts of time. By late 1944, American engineering doctrine had evolved to the point where bridge construction was treated as just another combat operation. Engineers would do reconnaissance before the infantry even arrived, identifying crossing sites and planning bridge approaches. As soon as the infantry secured a bridgehead, engineers would roll in with pre-staged Bailey components and start building. The goal was to have armor crossing within 12 hours of capturing a river crossing. This tempo was impossible for the Germans to counter. Their defensive doctrine assumed that rivers would provide at least 24 to 48 hours of security. Time to regroup, time to establish defensive positions, time to bring up reserves. American engineers were cutting that time to less than half a day. Defensive lines that should have been secure were being breached before the Germans could properly man them. The Battle of the Bulge in December 1944 proved the Bailey Bridge's value in another way: defensive flexibility. When German forces launched their surprise offensive through the Ardennes, they initially made good progress, partly because they captured several intact bridges before American forces could destroy them. But as the German advance slowed, American engineers were building Bailey bridges to channel reinforcements to threatened sectors. At Bastogne, surrounded by German forces, the 101st Airborne desperately needed resupply and reinforcement. The roads leading to Bastogne crossed multiple streams and rivers, several with destroyed bridges. American engineers built 8 Bailey bridges in 3 days, creating supply routes that allowed Patton's Third Army to relieve Bastogne. Without those bridges, the relief operation would have taken days longer, possibly too long to save the garrison. The Germans noticed. A captured document from January 1945, recovered from a German engineering unit, included this assessment: American rapid bridging capability is decisive factor in their operational mobility. Our bridge demolition efforts provide minimal delay. Recommend shifting defensive strategy to focus on terrain that cannot be bridged rather than relying on river lines. That's a complete reversal of German defensive doctrine. Instead of using rivers as defensive barriers, German planners were now telling units to avoid river positions because American engineers would just bridge them anyway. The Bailey Bridge had fundamentally altered the tactical calculus of defensive warfare. As American and Allied forces pushed into Germany in early 1945, the bridge building became even more impressive. The Rhine River, which German propaganda had described as an impassable barrier, was crossed in dozens of locations within weeks. Every crossing required bridges, temporary at first, then more permanent structures. Bailey bridges went up everywhere. The Rhine at Wesel was nearly 1,500 feet wide at the crossing site. That's way too long for a single Bailey bridge. Even the longest configurations topped out around 400 feet. American engineers solved the problem by building 3 separate Bailey bridges supported by intermediate piers constructed from sunken barges and debris. The whole structure was completed in 6 days, creating a crossing that could handle the entire weight of the 9th Army's assault divisions. German engineers examining captured Bailey bridge components were baffled by the simplicity. There was no complex machinery, no precision-manufactured parts requiring specialized facilities. Just steel panels with holes, pins to connect them, and basic hardware. A competent machine shop could produce these components. Yet the system worked flawlessly. Some German engineers argued that the Bailey Bridge was over-engineered, that the panels were heavier and stronger than necessary, creating excess weight. They were right, but they missed the point. The over-engineering meant the bridges were nearly indestructible under normal use. They could handle loads above their rated capacity without failing. They could take battle damage and keep functioning. The extra weight was a feature, not a bug. American combat engineer training emphasized speed and efficiency in Bailey Bridge construction. New engineers would practice on training courses, building and rebuilding bridges until they could do it in their sleep. By the time they reached combat units, they could identify components by touch in the dark, assemble structures without consulting manuals, and work under pressure that would crack most people. The engineers themselves were often overlooked in official histories. They weren't glamorous like infantry or armor, didn't have dramatic stories like pilots. But they were absolutely critical to American operational success. Every advance, every offensive, every breakthrough depended on engineers keeping the supply lines open. And that meant bridges. Sergeant Bill Davidson, who served with the 82nd Engineer Combat Battalion through France and Germany, later reflected, "We weren't heroes. We were just guys who knew how to build shit fast. But man, we were good at it. Give us a river and 12 hours, we'd have your tanks across. Give us 2 days, we'd have a bridge that could handle a whole armored division. The Germans kept blowing bridges, and we kept building new ones. Eventually, I think they gave up. Why bother destroying something that'll be replaced before sunset? That was the strategic reality. German bridge demolition, which should have been a decisive defensive advantage, became little more than an inconvenience. American engineering capacity had turned a major obstacle into a speed bump. By April 1945, as Germany collapsed, American engineers had built over 2,500 Bailey bridges in the European theater. Some were tiny, 10-foot spans over drainage ditches. Others were massive, multi-span structures over major rivers. All were built quickly, efficiently, and well enough to keep working under heavy use. The longest Bailey bridge built during the war was over the Rhine near Mannheim, 462 feet long, triple-triple configuration, rated for Class 70 loads. It was built in 31 hours by elements of 3 different engineer battalions working in shifts. German artillery targeted the construction site throughout the build, killing 7 engineers and wounding 23. The bridge was completed on schedule anyway. That bridge carried American traffic for 3 weeks before German forces in the area surrendered. After the war, it remained in use for civilian traffic until 1952, when it was finally replaced with a permanent structure. 7 years of heavy use. Not bad for something that was supposed to be temporary military expedient. The Bailey Bridge's legacy extended far beyond World War II. The basic design remained in military use for decades. American engineer units were still using Bailey Bridge sets through the 1980s. Modified versions are still used today in disaster relief and emergency situations. The fundamental principle, modular, interchangeable panels that can be assembled quickly without heavy equipment, proved so successful that it's still the standard for portable military bridging. After the war, surplus Bailey Bridge components flooded the civilian market. Thousands of bridges around the world, especially in developing countries, were built using ex-military Bailey Bridge sets. Remote areas that could never afford traditional bridge construction could assemble Bailey bridges with minimal equipment and expertise. The design that won the war ended up improving infrastructure globally. Donald Bailey, the mild-mannered British engineer who'd invented the system, received a knighthood after the war. Field Marshal Montgomery supposedly said, "The Bailey Bridge was the greatest engineering achievement of the war." General Dwight Eisenhower called it one of the 3 most important technological developments of the war, alongside radar and the atom bomb. That might seem like hyperbole. How could a bridge be as important as radar or nuclear weapons? But consider the strategic impact. Radar helped win the Battle of Britain. The atomic bomb ended the war with Japan. The Bailey Bridge enabled the entire European ground campaign from Normandy to Berlin. Without rapid bridging capability, the American advance across Europe would have been impossible. German river line defenses would have worked, and the war would have lasted months or years longer. The German generals who thought American engineers were crazy for trying to bridge major rivers overnight had been operating under outdated assumptions. They thought bridge building was slow, difficult, and required specialized equipment. The Bailey Bridge proved them catastrophically wrong on every count. A restored Bailey Bridge sits at the U.S. Army Engineer School at Fort Leonard Wood, Missouri. It's maintained as a training aid and historical artifact. Engineering students still learn Bailey Bridge construction techniques, not because they'll use this exact system in modern warfare, but because the principles of rapid modular construction remain relevant. Next to the bridge is a display case containing captured German documents from 1944 to 45. One document, a defensive planning memo from Army Group G dated November 1944, includes this passage: American engineering capabilities have proven far superior to pre-war estimates. Enemy forces can restore crossing capability over any river in 24 hours or less. River line defenses are no longer viable as primary defensive strategy. All defensive planning must assume enemy will achieve rapid crossing of water obstacles regardless of demolition efforts. That's unconditional surrender to American engineering superiority. The Germans had given up on bridge demolition as a defensive tactic because American engineers with Bailey bridges had made it pointless. Beneath the German document is a handwritten note from an American engineer who served in Europe. It reads, "They thought we were crazy. We thought we were just doing our jobs. Turns out, crazy works pretty well when you're building bridges at midnight while people are shooting at you. We weren't heroes. We were just stubborn bastards with wrenches and a pile of steel panels. But damn, we were good." That captures the essence of American combat engineering in World War II. Not fancy, not glamorous, just effective. The Bailey Bridge wasn't a technological marvel. It was just well-designed, well-built, and deployed by people who knew how to work fast under pressure. The German generals who dismissed American engineering as crazy had made the same mistake as German pilots who laughed at wildcats or tankers who mocked bazookas. They assumed that different meant inferior. They thought American methods were unsophisticated. They believed European military experience would trump American improvisation. They were wrong every time. The Americans didn't try to out-German the Germans. They didn't build better Panzers or faster Messerschmitts or more elegant bridges. They built Shermans by the thousands, Thunderbolts by the thousands, and Bailey bridges by the thousands. They played to American strengths: mass production, standardization, and the ability to turn simple designs into overwhelmingly effective weapons. The Bailey Bridge was peak American engineering philosophy. Make it simple enough that anybody can use it, tough enough that it'll work under the worst conditions, and cheap enough that you can make thousands of them. Then deploy it everywhere and watch your enemy's carefully planned defenses become irrelevant. By May 1945, when Germany surrendered, American engineers had demonstrated conclusively that bridge demolition was no longer an effective defensive strategy. Not because bridges couldn't be destroyed, the Germans had blown hundreds of them, but because American engineers could rebuild them faster than German forces could retreat to the next river line. The final statistics tell the story. American engineers built over 2,500 Bailey bridges in Europe, totaling over 250 miles of bridging. Some individual bridges saw more traffic in 6 months than most civilian bridges see in years, thousands of vehicles daily, including the heaviest armor. Failure rates were negligible. Maintenance requirements were minimal. The system worked exactly as designed under conditions far worse than anything the designers had anticipated. German engineering officers captured in 1945 were extensively debriefed about their demolition strategies and why they'd failed. A common theme in their responses was disbelief at American bridging speed. One Oberst, who'd overseen demolitions along the Moselle River, said, "We destroyed every bridge. Every single bridge. Within 2 weeks, the Americans had rebuilt them all. Not temporary crossings, permanent bridges capable of supporting heavy traffic. We couldn't understand it. Our intelligence had no information about such capabilities." Another German officer, when shown Bailey bridge components and asked for his assessment, examined the pieces for several minutes before responding, "This is genius. Stupid genius, but genius. Any fool can assemble this. That's the point, yes? You don't need clever engineers or specialized equipment. Just strong backs and time. And Americans have both in abundance. We tried to be clever with our demolitions. You were clever with your bridges. In war, clever defense loses to clever offense." That last line is worth remembering. The Germans had been very clever with their defensive engineering, sophisticated demolitions, well-planned fallback positions, intelligent use of terrain. But American offensive engineering was better. Simpler, faster, more sustainable. The Bailey Bridge didn't just solve the river crossing problem, it made the problem irrelevant. The scale of Bailey Bridge deployment in Europe was truly staggering when you break down the numbers. Between June 1944 and May 1945, American engineer units constructed an average of 7 Bailey bridges per day. 7 bridges. Every single day. For 11 months straight. That's not counting British and Canadian engineers who were building their own Bailey bridges simultaneously. Consider what that means operationally. Every week, American engineers were adding roughly 50 new river crossings to the European road network. Every month, over 200 crossings. The Germans couldn't possibly destroy infrastructure faster than the Allies could rebuild it. The mathematical impossibility of the situation must have been soul-crushing for German logisticians. The bridges weren't just being built, they were being maintained under combat conditions. Engineers established bridge companies, whose sole job was to repair and maintain existing Bailey bridges. These units would patrol their assigned bridges, replacing damaged panels, reinforcing approaches, and keeping traffic flowing. Some bridges were under near-constant artillery harassment but remained operational for months. Captain Robert MacDonald, commanding a bridge maintenance company in the 9th Army sector, kept detailed logs of his unit's activities. His records from March 1945 show that his company maintained 14 Bailey bridges simultaneously, conducted 47 panel replacements due to combat damage, and kept all bridges operational with 99.8% uptime. That's better than most peacetime civilian bridges. The complexity of the logistics behind Bailey bridge operations was mind-boggling. Each bridge required specific components based on length, load rating, and site conditions. Engineers needed accurate measurements of the gap to be spanned, soil conditions for approach construction, water depth and current for foundation planning, and expected traffic loads. American engineer units developed specialized reconnaissance teams that would move with advancing forces, surveying potential crossing sites and radioing back requirements. By the time the main engineer units arrived, they already knew exactly what components they needed and where to position them. This forward planning cut construction time significantly. The component supply chain was equally impressive. Bailey bridge panels, stringers, transoms, and hardware were stockpiled at forward supply dumps, organized by type and ready for immediate dispatch. Truck companies were dedicated solely to hauling Bailey components. Some convoys carried complete bridge sets, everything needed for a specific bridge configuration loaded in the correct sequence for efficient unloading. Technical Sergeant James O'Brien, a supply specialist with the 1st Army, described the system. "We had it down to a science. Engineers would radio their requirements. Say, a 140-foot triple-double bridge. We'd pull the manifest, load the trucks in assembly order, and have that shipment rolling within 2 hours. The engineers could start building as soon as the trucks arrived because everything was sequenced perfectly. First truck has approach components, second truck has the initial panels, and so on. No sorting, no figuring, just unload and build." This level of logistical sophistication wasn't luck. It was the result of American industrial organization applied to military operations. The same principles that made American factories so productive, standardization, interchangeable parts, assembly line thinking, were applied to combat engineering. The result was a system that could scale massively without breaking down. The Germans, watching this unfold, couldn't replicate it even when they captured Bailey bridge components and studied the system. It wasn't that German engineers couldn't understand how Bailey bridges worked. The design was brilliantly simple. The problem was that Germany's industrial base was being systematically destroyed by Allied bombing, and their supply lines were constantly harassed by air attack and partisan activity. Even if German factories could produce Bailey-type components, and some tried, getting them to the front lines was nearly impossible. American convoys moved freely in daylight with air superiority protecting them. German supply convoys had to move at night to avoid Allied fighter bombers, and even then faced constant interdiction. A bridging system is only useful if you can deliver the components where they're needed. The air superiority factor can't be overstated. American engineers could work in broad daylight, often with fighter bomber support on call to suppress German artillery. German engineers had to work at night under blackout conditions, constantly worried about Allied air attack. This gave American engineers an enormous time advantage. They could work around the clock in shifts, while German engineers were limited to darkness. There were instances where American fighter bombers would actively defend bridge construction sites. At the Roer River in February 1945, German artillery was hammering an American bridge site so effectively that construction had stopped. The engineer commander called in air support, and P-47 Thunderbolts from the 9th Air Force arrived within 20 minutes. They located the German gun positions and destroyed them, allowing construction to resume. The bridge was completed that afternoon. German forces rarely had this kind of responsive support. The Luftwaffe was mostly grounded by 1945, fuel shortages limiting operations to critical missions. German engineers were on their own, which meant they worked slower, took more casualties, and completed fewer bridges. The human element of Bailey Bridge construction deserves more attention. These weren't specialized bridge-building experts. They were regular American soldiers, many of them draftees who'd been civilians 18 months earlier. They learned bridge construction in training camps in the States, practiced on courses that simulated combat conditions, and then applied those skills under actual fire in Europe. Private Leonard Schwartz, from Brooklyn, New York, had been a department store clerk before the war. By March 1945, he was a squad leader in an engineer battalion, directing bridge construction like he'd been doing it his whole life. The training was good, he recalled, but nothing really prepares you for building a bridge while people are shooting at you. You just focus on the task. Panel goes here, pin goes there, hammer it in, move to the next one. Don't think about the shells landing. Don't think about the guy next to you who got hit. Just keep working. The faster we build, the faster we're done and out of there. That mentality, focus on the work, ignore the danger, trust your training, was common among American combat engineers. They understood that hesitation meant prolonged exposure to fire. Speed was survival. So they worked with organized intensity that impressed even hardened infantry veterans. The physical demands were brutal. Bailey panels weren't incredibly heavy at 570 pounds. 6 men could carry one. But doing it repeatedly for hours while wearing combat gear on muddy riverbanks, often at night, sometimes under fire, was exhausting. Engineers would work until they literally collapsed, be given a few hours to rest, then get back to it. At the Saar River crossing in December 1944, one engineer battalion worked for 38 consecutive hours building a bridge in freezing rain. Men were falling asleep while carrying panels. The battalion commander finally ordered mandatory rest periods after 3 soldiers fell into the river from exhaustion. Even then, the bridge was completed in 42 hours, well ahead of schedule. The winter conditions in Europe during 1944-45 made bridge construction especially difficult. Frozen ground made approach construction harder. Ice on the river created additional hazards. Metal components became dangerously slippery and painful to handle with bare hands. Yet American engineers maintained their construction pace throughout the winter. German defenders, watching American engineers work through conditions that German troops considered prohibitive, drew conclusions about American determination that weren't entirely positive from the German perspective. If the Americans would build bridges in blizzards under artillery fire, what wouldn't they do? The Bailey Bridge also solved specific tactical problems beyond just river crossings. Engineers used Bailey components to create elevated roadways across flooded areas, to reinforce damaged permanent bridges, and even to construct defensive positions. The modular nature of the system meant it could be adapted to almost any engineering challenge. In the Hurtgen Forest, where heavy rain had turned roads into impassable mud, engineers laid Bailey panels flat to create corduroy roads that could handle heavy traffic. In urban areas, Bailey panels were used to bridge rubble-choked streets, allowing vehicles to bypass destroyed sections. At the Remagen bridgehead, when the Ludendorff Bridge collapsed, engineers had traffic rerouted to Bailey bridges within hours because they'd anticipated the failure and prepositioned components. This adaptability multiplied the Bailey Bridge's value. It wasn't just a river crossing tool, it was a general-purpose engineering solution that could be applied creatively to various problems. American engineers became adept at improvising uses for Bailey components that weren't in any manual. Technical Sergeant William Chen, a Chinese-American engineer from San Francisco, developed a technique for using Bailey panels to create blast walls protecting bridge approaches from artillery. By stacking panels vertically and filling the space behind them with rubble, he created barriers that could absorb artillery hits while still allowing traffic to pass. His innovation was adopted across multiple engineer battalions. The cultural aspect of Bailey Bridge construction also matters. American soldiers came from a society where construction and building were valued skills. Many had worked construction jobs before the war, were familiar with blueprints and technical drawings, and understood structural principles. This made them naturally suited to combat engineering. Additionally, American military culture emphasized initiative and improvisation. When the manual said a bridge should take 12 hours and circumstances demanded it be done in 8, American engineers would figure out how to do it in 8. They'd modify procedures, reorganize work parties, and find efficiencies that training manuals hadn't envisioned. German military culture, while highly professional, was more rigid. Procedures were followed precisely because they'd been proven to work. This meant German engineers were very good at executing established procedures but less flexible when circumstances demanded improvisation. American engineers excelled at improvisation, sometimes to a fault. There were instances of American-built bridges that violated every engineering principle yet somehow stayed up and functional. The relationship between combat engineers and frontline infantry was interesting. Infantry troops quickly learned to respect engineers once they saw what engineers could do under fire. There's a famous photograph from the Roar River crossing showing infantry soldiers helping engineers carry Bailey panels. Infantry volunteering for heavy labor because they knew the bridge meant they could get armor support and continue advancing. This mutual respect was built on shared combat experience. Engineers weren't rear echelon troops, they were up front with the infantry, often ahead of the infantry securing bridge sites. They took casualties, fought when necessary, and earned their place in the line. Infantry learned that engineers were reliable, tough, and critical to mission success. German defensive planning in late 1944 and early 1945 increasingly focused on trying to destroy Bailey bridges after they were built rather than preventing construction. Artillery observers would watch for bridge construction, let it complete, then call fire on the finished bridge hoping to catch it full of traffic. This was marginally more effective than trying to stop construction, but still didn't solve the fundamental problem. American engineers would just rebuild. There are documented instances of the same river crossing being bridged 3 or 4 times as German artillery destroyed successive Bailey bridges. Each time, American engineers would clear the debris and build again. Eventually, German artillery would run out of ammunition or be forced to displace by advancing American forces. The Americans always got their bridge in the end. The psychological warfare aspect was significant. German defenders who watched Americans build bridge after bridge, despite constant artillery harassment, must have felt a sense of hopelessness. If the enemy could casually rebuild infrastructure under fire faster than you could destroy it, what hope was there of stopping them? Some German units developed a dark humor about Bailey bridges. A captured diary from a Wehrmacht soldier defending the Rhine in March 1945 included this entry: "The Americans finished another bridge today. That makes 3 this week just in our sector. Our artillery hit one yesterday. They rebuilt it overnight. It's like fighting ants. You kill one, 10 more appear. Except these ants build bridges." The strategic implications of Bailey bridge capability extended beyond immediate tactical advantages. American operational planning could assume that river obstacles were temporary delays, not campaign-stopping barriers. This meant offensives could be planned with aggressive timelines that would have been impossible without rapid bridging. Patton's famous dash across France in August 1944 was possible partly because his staff knew that engineer units could bridge any river his armor encountered. Patton could push his spearheads forward without worrying about maintaining intact bridges behind them. Engineers would build new ones as needed. This operational tempo was unprecedented and completely disoriented German defensive planning. The Germans, conversely, had to plan their retreats around preserving bridges until the last possible moment, then destroying them as they withdrew. This constrained their operational flexibility. They couldn't retreat as quickly as Americans could advance because they needed to maintain infrastructure longer. By April 1945, as the war entered its final weeks, Bailey Bridge construction had become so routine that it barely rated mention in after-action reports. Built bridge across X River, completed in Y hours, was a single-line item in daily logs. What would have been a major engineering achievement in 1943 was routine business in 1945. The professional development of American combat engineers during the war was remarkable. Units that struggled with basic construction in 1943 were executing complex bridging operations with casual efficiency by 1945. The 291st Engineer Combat Battalion, for instance, reduced their average bridge construction time by 40% between their first bridge in 1944 and their last bridge in 1945, while working under increasingly difficult conditions. This improvement came from experience, yes, but also from a culture of learning and adaptation. Engineer units would share techniques, study each other's methods, and incorporate improvements constantly. There was healthy competition between battalions to see who could build the fastest bridge, which drove innovation and efficiency. Today, military historians recognize the Bailey Bridge as one of World War II's most important innovations. It doesn't get the attention of tanks or aircraft, but its impact on the war's outcome was arguably greater. Without rapid bridging capability, the American advance across Europe would have been impossible. German defensive strategies would have worked. The war would have dragged on, possibly into 1946 or beyond, with incalculable additional casualties. The strategic calculus is brutal but clear. Every day the war continued meant thousands more deaths on all sides. The Bailey Bridge, by enabling rapid Allied advances, helped end the war months earlier than it might have ended otherwise. That's thousands of lives saved, Allied soldiers, German soldiers, and civilians caught in combat zones. Donald Bailey died in 1985, mostly forgotten outside engineering circles. But his invention had changed warfare fundamentally and permanently. The principle he established, that complex military problems could be solved with simple, modular, mass-produced solutions, became a cornerstone of American military doctrine. Modern American military logistics is built on this foundation. Identify the requirement, design a simple solution, mass-produce it, distribute it widely, and trust trained personnel to use it effectively. The Bailey Bridge influenced post-war engineering in ways Bailey never anticipated. The modular construction principle was applied to prefabricated buildings, emergency shelters, and temporary structures of all kinds. The idea that complex structures could be assembled from simple, interchangeable components became standard practice in construction and manufacturing worldwide. In developing countries, surplus Bailey bridges became critical infrastructure. Thousands of bridges built from ex-military components still carry traffic today, decades after the war. Remote communities that could never afford traditional bridge construction could assemble Bailey bridges with minimal equipment and training. Bailey's simple design literally connected isolated communities to the modern world. The German generals who thought American engineers were crazy learned a hard lesson. Crazy wasn't building bridges overnight. Crazy was thinking you could stop the Americans by destroying bridges. Crazy was underestimating American engineering capacity and determination. Crazy was assuming that traditional defensive strategies would work against an enemy with unlimited industrial capacity and the will to use it. The Americans weren't crazy. They were just better prepared, better equipped, and better at turning industrial capacity into battlefield advantage. The Bailey Bridge was the perfect example, an unglamorous, unsexy piece of equipment that nonetheless proved decisive in the European campaign. By the time German generals figured this out, it was too late. The American army was already across every river in Europe, rolling toward Berlin on roads kept open by engineers who could build bridges faster than the Germans could blow them up. The strategic situation was hopeless for Germany not because of any single defeat, but because of systemic American advantages in logistics, engineering, and industrial capacity. The laughter stopped somewhere around September 1944, when German commanders realized that river lines weren't slowing the American advance at all. By January 1945, the laughter had turned to frustrated disbelief. How could the Americans be doing this? By April 1945, it had become resigned acceptance. The war was lost, and German soldiers knew it. The final irony is that some German engineers tried to copy the Bailey Bridge design for their own use in early 1945. Several German engineering units fabricated crude imitations of Bailey panels using captured components as templates. But by then, Germany's industrial capacity was so degraded that they could barely produce enough components for 1 or 2 bridges. Meanwhile, American factories were producing enough Bailey components for dozens of bridges weekly. A German engineering officer, captured in April 1945 and interviewed about his unit's attempts to copy Bailey bridges, gave this assessment: "We understood the design. It's not complex. Any competent engineer could replicate it. But understanding something and being able to mass-produce it are different problems. You Americans don't just build good weapons, you build enormous quantities of good weapons. That's why you won. Not because you're better engineers than us, but because you have 100 engineers for every one of ours, and factories that can produce 100 bridges while we produce one." That analysis was accurate. American victory in World War II wasn't primarily about tactical or technological superiority, though Americans had plenty of both. It was about systematic advantages: industrial capacity, logistical sophistication, resource availability, and the organizational ability to apply those advantages effectively. The Bailey Bridge embodied all of these advantages in one simple, elegant system. The crazy American engineers with their simple bridges had won. And the German generals who'd planned their entire defensive strategy around bridge demolition had lost. Not because American engineers were somehow superhuman, but because they had the right tools, the right training, and the industrial backing to keep building no matter what the enemy did. At the end of the day, war is about logistics. Armies don't fight on inspiration and courage alone. They fight on fuel, ammunition, food, and the ability to move forces where they're needed. The Bailey Bridge gave Americans a decisive logistics advantage that German forces couldn't counter. It kept armies moving, kept supplies flowing, and kept the pressure on German forces constantly. There's a memorial at Fort Leonard Wood, Missouri, honoring American combat engineers who served in World War II. Next to it stands a preserved Bailey Bridge, maintained in working condition as both memorial and training tool. The plaque reads, "In memory of the American combat engineers who built the roads to victory. They built under fire, they built under pressure, and they built bridges that armies crossed to freedom." That's the legacy of the Bailey Bridge and the men who assembled them. Not glory, not headlines, just essential work done well under impossible conditions. The kind of unglamorous competence that wins wars. Turns out, sometimes the craziest thing you can do is underestimate the Americans' ability to build shit really, really fast. The Germans learned that lesson the hard way. By the time they figured it out, American engineers had already built the bridges that carried Allied armies from Normandy to Berlin, and the war was over.